before I forget. It's important. Okay, so other homework questions while we're at it. It's due Monday night. Homework question emails are always welcome. So remember, if you get stuck on something for more than 15 minutes, please send me a screenshot of your error or how you think you've solved the problem that the system is not taking, and I will try to do my best to help troubleshoot. Good? Okay. In off-topic announcements, I wanted to show you this. I found this yesterday at Walmart. It is a new flavor of Diet Mountain Dew. It is raspberry lemonade flavored Diet Mountain Dew, and it is excellent. So I just wanted to share, because historically Diet Mountain Dew has come in green flavor, like whatever the standard flavor is, and red. Code red is also excellent, by the way. But this is the first Diet Mountain Dew of another color, so it's very exciting to me. Thought I'd share that. Highly recommend. The other thing I thought I'd share is that I updated the syllabus this morning, and in keeping with the other class, I decided to bump the due date for what was homework 3, was going to be due right after spring break, to be 1 week later. So I don't know what I was thinking, trying to have something due the Monday right after we come back. I decided that that was a terrible idea. So just a minor adjustment to the syllabus. We'll have homework 1 due on Monday. You'll have a formative assessment the following Monday, and then this homework 2, based on the example we're starting today, will be after that. So I will let you know when the next things are available. They're not ready yet because I'm waiting to see how far we get to make sure that you'll be able to answer the questions. As it turns out, I figured out this morning that I have been teaching for 18 years, and I am still terrible at predicting how long things are going to take. I have never once gotten it anywhere close to right. So the syllabus continues to adjust throughout the semester because I want to make sure that whatever I ask you to do is something that we've covered in enough depth that you'll be able to do it. So I apologize for the amount of uncertainty that that introduces, but what I can promise is that the due dates will always go farther in time. They will never, ever be sooner than expected. Because even if I'm wrong in that direction, I won't make it due any earlier. So just wanted to share that. Then if we don't have any homework questions or schedule questions, then we can start talking about new stuff. How does that sound? Sound excellent? Yes. Okay, can someone on Zoom please say hello so I can check the audio on the recording?
Hello.
Thank you. All right. So are we excited? Our first actual generalized linear model. So we went over sort of the idea of how these are going to work at the beginning of the semester. And now it's time to get into the nitty-gritty in terms of the details of how each of the types of outcomes that we're going to predict are predicted using a link function, some other conditional distribution, and the regular old linear model that you're used to. So this unit, binary and categorical outcomes. As crazy as this sounds at the outset, I will tell you, the easy part of this unit is going to be the X side. How to interpret a main effect, how to interpret an interaction, what's a slope, what's an intercept, all that stuff is going to be the same. What the hell Y is going to be the hard part. Because each of these models is set up a little bit differently with what exactly you're predicting, and then you have to worry about the scale you're predicting it in. So the complexity that is introduced in changing from a continuous outcome to a categorical outcome lies in entirely how are you characterizing exactly what the model is predicting. So that's my setup, my caveat for what we have to share. All right. Nope, doorbell not done yet. Okay. There we go. Ta-da. So first off here, 3 parts of a generalized linear model, broadly speaking. Some other kind of distribution for what the outcome residuals look like, or what we would call the conditional distribution, meaning what is left over after putting in the model predictors. A link function, and a linear predictor. So I have in here in parentheses fixed and random effects, because if you use these models with multi-level data, such as longitudinal data, or individuals clustered in groups, the linear predictor includes fixed effects and random effects in those cases. So we're not talking about random effects yet in this class, but I wanted to put that out there for those of you who've seen those sorts of models before. So first part here, non-normal conditional distribution of y. So general linear models, what we just finished reviewing, what we know of as ANOVA and regression, they all share the idea that the y that is left over after the predictors have their effects is supposed to be normally distributed and have constant variance. That's the part that we're changing. It is also the case that general linear models assume independent residuals, and that is still the case in these models. So generalized models are single-level models for independent observations. The second half of this class is focusing on how they get extended to multivariate cases, when you have more than one outcome per person, such that those outcomes would have a correlation in them. So for now, we're sticking with independent outcomes, single-level modeling. So in the case of continuous outcomes, let's say continuous outcomes that are roughly symmetric, not horribly skewed or anything like that, the normal distribution for the residuals works pretty well. And there's been a lot of research suggesting that it's not so bad, and it might be better than some other alternatives that you have the chance to get wrong. So it's kind of like the workhorse of regression type modeling. But for a lot of types of outcomes, there is no way that the residuals can be normally distributed. It just cannot happen. So the question is, what is more plausible as an alternative shape for what the residuals would look like? In other words, what is an alternative formula by which we can compute a height using a likelihood function? So for categorical outcomes, such as what we're talking about in this unit, bounded outcomes, so things like percentages where you can't go below 0 or above 1, or counts where you can't go below 0, or things that are skewed, which a lot of times can't go below 0. Other types of distributions are going to be more plausible. And so what we do is maximize the likelihood of a distribution that better fits the data in those cases. The reason that this matters is to make sure that the standard errors that we have for our fixed effect are as accurate as possible. The standard errors come from our model for what the residuals look like. So if we assume that the residuals have constant variance, for instance, then we can end up with fixed effect standard errors that are either too small or too big, depending on how the model has non-constant variance. So one size doesn't necessarily fit all. And so we want to make sure that we pick a distribution that better fits what the actual outcome could look like. And one thing that's tricky about this is that most of the distributions we're going to see in this class are not actually going to have a separately estimated residual variance. That is a unique feature of normal that doesn't show up in others. So for instance, the binary outcomes that we're starting with, a Bernoulli distribution has no separate variance to it. The only parameter in it is a mean. The same thing is true for count outcomes that follow a Poisson distribution. There's no separate parameter for the variance. I will note that if you're following along with the Agresti textbook that's part of your readings, he refers to this idea of what the conditional distribution is of y as the random component. That is a terrible phrase because it is not the same thing as random effects. So by random, he means error, like residual, leftover, unknown. Like put those words in instead because it's not about random effects. I had a question, by the way, from someone about that book in particular, and the question was, should I understand that book? And the answer to that is no. That book is hard. But I wanted to include it to provide balance in the reading material, because a lot of what I suggested for the reading list were tutorials and examples, and the Stata book is very heavily example focused, and the Agresti book is more theoretical. He also talks about things that are more general, like what's the difference between a likelihood ratio test and a Wald test and a score test, and those kinds of things that are a lot more technical and not applied. So I wanted to put that book in the mix so that you would have that background. But if you're reading it and you're like, yeah, I don't know what the hell any of this is, you're in good company. That is my reaction to a lot of it. So just to be fair, it's not easy. But eventually it will get easier, is what I can say about that. All right, so in addition to what kind of outcome distribution are we going to use instead of normal, what's the link function? So a link function is a transformation of what the model predicts. It is a transformation of the conditional mean to be predicted so that the outcome to be predicted by the model is unbounded, continuous, and goes on forever. So it's very easy to get this idea confused with just transformations to the data. So one of the things that may have been covered in your earlier stats classes or badly in certain textbooks is the idea of transforming data. Like, well, everything has to be normal, so take the square root of it or take the log and make it normal. You don't have to do that. And in fact, doing that outside the context of a model is a terrible idea. So we're not talking about transforming data. We're talking about a transformation of what the model is actually predicting that happens inside the model. So for instance, in this unit, we're predicting binary outcomes, 0 or 1. We are not touching those. The original column of data that serves as y with respect to our model code is the 0s and 1s. The link function happens internally within the estimation. So a link function is how you go from the outcome to be predicted to the continuous version that the model is then predicting. The opposite of that is known as an inverse link. And it's how you go from what is being predicted by the model back into the scale of the original data. So you will see these words in some of the slides. You'll see them in software documentation. Link is from data to model. Inverse link is model back to data. So what happens then is that once you transform the outcomes from the model, use the inverse link to get back to the data, they obey the boundaries of the data. So the link function's job is to create something that's unbounded, yet still when you back translate, make it a plausible prediction that stays in bounds. So for instance, if I'm talking about a binary outcome, what the model is trying to predict for each person is the mean. The mean of the binary outcome is the proportion of people who have a 1. In other words, we're predicting the probability of a 1. That's the conditional mean that's being predicted. So the data are 0, 1. The conditional mean is the probability of a 1. But if I try to predict probability directly, it's not going to work because the model needs to understand that probability cannot go below 0 and it cannot go above 1. So we need a transformation of probability that allows it to stretch and become unbounded so that a linear model can then predict it. For a count outcome, as another example, the link function people use for count outcomes is almost always the natural log. By the way, in this class, there is no log base 10. If I say log, it's natural log. E to the whatever, that thing. I'd have to look up the definition on Wikipedia to not screw it up. I don't have it at the top of my head, but it's natural log, that one. So the log link for count data makes it so that the log of the count, when you predict that, goes on forever and ever in both directions. But when you unlog it, when you take the inverse link to go back to counts, it stops at 0. So it keeps it from predicting negative counts. So a link function controls the range of the values basically to be predicted so that they fit with the actual data.
I have a quick question. So,
hit me.
So let's say that we have it's a case where maybe it's a linear, there's a linear relationship that seems to be at play, but then there's outliers because that's what I've also heard transformation being applied to is to bring some of those outliers back into range.
Yeah.
So would you also recommend not doing that?
So that's a different problem with a different solution.
Okay.
The concern about, so for more continuous outcomes, the concern about outliers is that they're going to have undue influence on the regression line. And you get into very subjective territory real quick if you want to start arbitrarily kicking out data points because they look too weird. because someone else is going to have a different cutoff for where too weird is. And in general, I think if it's a data point that is believable, you have no business removing it. If it changes the results that much, I think then you owe the audience a description of what happened with them and without them so they can decide for themselves which they want to believe in. The solution to that problem, though, is the exact same solution that you would have learned in intro statistics with respect to describing central tendency. If you have a distribution that's highly skewed or has outliers or something, the mean is not a good estimate of central tendency. What do you use instead? What's a more robust version of central tendency that's not as susceptible to outliers? What was it? That's dispersion, not central tendency. It's another word that starts with an M. Median. We got a couple, median, yep. So in that same vein, you can set up a regression model that predicts the conditional median instead of a conditional mean, so that that prediction is less susceptible to the influence of outliers. And regressions that predict medians instead are called quantile regression. And given that the median is the 50th percentile, you can actually predict any that you want. So unit, doing the math, 4, I think example 4b is going to be a quantile regression to demonstrate this exact problem that you just asked about. So what do you do if you have outliers? You don't change the data, you change the model. That's always going to be my answer to the question, by the way, is leave your data alone and find a better model. Thank you for the question. But in the case of binary data, there is no such thing as an outlier, right? It's either a 0 or 1. Okay.
I had a follow-up question.
Hit me.
So you're just saying obviously don't change the data. I can imagine lots of reasons for that. But if you were trying to convince someone like this is a bad idea, one of the reasons to not do it, like some of the reasons would be like, other than the fact that you're completely changing the data, so you're like modeling something different, but you could mess up like the scaling of it, the relationship between like the data and the model, and then the conditional mean / predicted outcome. Is that true?
I would say yes. There are certain circumstances in which a transformation can be used as a trick to create a nonlinear prediction. So for instance, if you're modeling something like you have, let's say, an experimental set of trials where you make somebody do the same thing like 500 times and see how fast they can do it, they're going to get better, like response time's going to come down real quick and then it's going to hit some kind of asymptote until they get bored, right, and they start sucking and then it goes back up again. But assuming that they're still paying attention, if you take the order of the trial and do a natural log transform on that, then the linear effect of log transform trial order actually then creates an exponential function. So transformations can be used to create different shapes that can still be modeled using a standard linear model, because it turns out that an actual nonlinear model, like that's nonlinear in the parameters, is way harder to fit, way harder to find software for, and more likely to have non-convergence. So there are tricks that you can do involving transformations to make it look like it's a nonlinear model. But in general, if I wouldn't just transform an outcome like just as a standard because it's not normal enough. Because like if I transform, say, if I change response time to a natural log response time, then any slopes that predict response time are actually exponential slopes. They're not linear. If you're okay with that, then okay, but it's not the same model anymore. So I think that's what you're getting at, Andrea, about like it's a different relationship between the variables and the predictions at that point.
Yeah, that articulated it better though. Thanks.
You're welcome. It's all about the do. The raspberry lemonade is giving me some extra skill today. I can feel it. All right, other questions? No? Okay. So you might be thinking to yourself like, well, why haven't I heard about this link function thing before? And the answer is you have. By the way, what you know of as a general linear model is a special case of a generalized linear model that uses something called an identity link, meaning leave it alone. because its outcome is already supposed to be continuous. So can I share with you a quick story? Yeah, it's sort of a rhetorical question whenever I say that, but it's like my way of saying I'm changing the topic just ever so slightly. So I wanted to show you a real-life bummer of an identity link. This is a scratch-off card, as it is known at my house. This is a lottery ticket that you can buy at a gas station. They sell them in almost every state, and you can buy them starting from $1 up to lottery tickets that are like $20, I think now. I think that was the most expensive one I've seen. Can anyone confirm? Can you get scratch-off tickets that cost more than $20? Yeah, they're low-end risk, but this one was purchased in South Carolina, where I spent Christmas with my family, and my family has a tradition of putting lottery tickets in our stockings. It's a thing that we've done ever since I was a kid. Even though gambling is illegal for children and all that, I scratched off these tickets as a child. So we went to the gas station, got some scratch-off tickets for Christmas morning. We all sat there, after opening presents, scratching these off. And this one is bingo. And the premise of this is exactly like the game bingo, where you have a letter and number combination, and then you go down your playing cards and you scratch off everywhere that has this particular instance. So O75, for instance. I go down my O columns. There's one right there. There's another one. So I go all the way through my numbers, and I hit a bingo. So this one right here, I read the fine print, and it says that I won $10, but then it says, check your multiplier. Like, how much more did you win? And so I scratch off my multiplier, and wah, wah, it's 1x, 1 times. So I only won $10. But I saw this, and I was like, oh my God, this is a perfect example of an identity link. I have to take a picture of this for my spring class. And my family was like, Lisa, it's Christmas morning. What are you doing? But this is immediately where my head went. So this is a real-life bummer of an identity link. How's that? But I got the $10, so I don't think we broke even, but we got reasonably close to even this year, which I think is better than most years. So anywho. So not normal conditional distribution. We pick something that matches what the data values actually can be. Link function, we let the model create an unbounded outcome to be predicted, and then the regular old linear model that you're used to works just like it's supposed to. So in the link transformed outcome, an intercept is an intercept, a slope is a slope, and everything is beautiful. So if I'm predicting, say, a binary outcome, the link function that we're going to use, which we'll talk about in detail today, is known as a logit. So I would predict the logit of the probability of a 1 directly, but the inverse link function, the reverse of it, basically gets me from logits back to probabilities. So I would predict the logit and then back translate that into a predicted probability. Likewise, for count data, that's the next unit, we'll predict the log of the expected count as the link function, but then you can back translate through inverse link to go from log count back to expected count. And software will do most of this for you. So the benefit of this system is that the linear model parameters are interpreted in the same way that you're used to. The switch is just in how you talk about y. So rather than saying the intercept is the expected outcome when all the predictors are 0, you would say the intercept is the expected logit when all the predictors are 0. Or it's the expected log count when all the predictors are 0. So it's just an adjustment in the scale of y that the linear model is predicting. And then one aside here, the fixed effects. So the solution for what the fixed intercept and any fixed slope would be in a general linear model is not something that has to be searched for iteratively through the likelihood. So in general models with only a single residual and in general mixed models that have random effects and a normal residual, literally there's a formula that once you know what all the variance estimates should be, the fixed effects fall out of that. They do not have to get found, they are determined. The consequence of that in general models is that you really can't break a model by adding too many predictors. Whereas in these models, the fixed effects are no longer determined. They have to be searched for in the same iterative process of trying to make the data the tallest with all the model parameters. They count as model parameters. So that means that it is possible to run into convergence problems in these models, meaning that it just doesn't work, it doesn't give you the answers back, it just gives up. If you have too many predictors or predictors where you get into situations of complete redundancy. So that happens if you have categorical predictors a lot, like if you don't have every combination of zeros and ones across a series of categorical predictors, the model can get hung up on trying to figure that out. So just a word to the wise in terms of troubleshooting. Fixed effects can cause problems too now. Okay, how are we doing? Questions? No? Okay. So we looked at this like 3 weeks ago, but I thought it would be relevant to go over again since we're talking about binary models. So to make this a little more concrete, let's say that we are trying to predict a binary outcome. So if I don't know anything else about a person, my best guess for their outcome is still going to be the mean. For a binary outcome, the mean to be predicted is the probability of a 1. So like the proportion of ones, basically. So one thing I want to note is that the conditional mean has many more possible values than the outcome. The outcome is still 0, 1, but all of the proportions along the way are potential conditional means. So what if I just say, yeah, I don't need generalized linear models. I'm just going to throw this thing in a regression and hope for the best. And in fact, there are actually papers that have been published relatively recently advocating for this approach. I don't know why. I think it's a terrible idea, but it can be done, that you can submit a 0, 1 outcome variable to a regression and not change a darn thing. So let's see what would happen if I do that. Well, beta 0 would become the expected probability of a 1 when all my predictors are 0. Each of these beta slopes would tell me the expected change in the probability for a unit change in the predictor. And then the E residual would pick up the difference between the observed outcome, which is 0 or 1, and the predicted outcome. So what could go wrong? Well, number 1 is the slope. A linear model means a line. A line keeps going. So if I put in a slope of x to predict a binary outcome, even though what I'm predicting is the probability of a 1, I still run into the problem that the model does not understand that probability needs to shut off. It would predict probabilities above 1 and below 0. So we can't want that. What we need is for the line to obey this kind of curve to it instead. We need for the line to understand that it can't go past 1 and that it can't go past 0. So this particular shape, this kind of S shape, is known as a logistic shape. And yes, IRT folks, there's like 6 slides at the end of this that are for you. I don't know if I'll have a chance to go over them in class, but if I don't, I will make a separate recording because yes, this is IRT. We've wandered into that territory. So what do we do instead? So step 1 is to transform the conditional mean probability of a 1 into something called odds. Now, this is something I was very sloppy about in my wording and notation for many years, and I'm trying to do a much better job. Do you see how this is p over 1 minus p? And that's a ratio? This is not an odds ratio. Odds is a ratio, but odds ratio is not this. It's another thing. And I used to use those terms somewhat interchangeably because to me, this is a ratio. What are you talking about? No, it's not. It's not an odds ratio. This is just odds. So it's the probability that you got a 1, according to the model, over the probability that you got a 0. So if your predicted probability of a 1 is 0.7, the odds of you getting a 1 are 2.33, and the odds of you getting a 0 instead, if you take the reciprocal of this ratio, would be 0.4. So in terms of creating an outcome to be predicted that's more continuous, we're halfway there. Because odds goes on into positive infinity, but it's truncated at 0. So then some genius figured out that if you take the natural log of this thing, the natural log of the odds of the probability of a 1 is what's known as a logit. And that thing is symmetric at 0 and unbounded in both directions. It goes on until positive to negative infinity. So I say logit. You will also see this written as log odds. So that is a term that's more common in medicine, for instance. It means the same thing. This is the one where my former graduate student says it's a logit because you're taking the log of it. And I said that seems to work too. So it's logit or log odds. So this is the new metric. This is the new y hat to be predicted, is this thing. The log of the odds of the probability of a 1. Okay. Say it with me, folks. The log of the odds of the probability of a 1. No one's saying it. Can you hear me? Okay, one more time. Hang on, I got my stick. I have a stick. I have a pointer stick. I'm a conductor. Okay, ready? The log of the odds of the probability of a 1. You got to commit that to memory. That's what a logit is. The purpose of a logit is to turn probability into something that is continuous to be predicted. So I got some pictures here. So we're talking about now 2 different ways of describing how the model predicts an outcome. It predicts it in probability, indirectly. It predicts it in logits, directly. So you will see these words too thrown about. If people say, oh, this is in the data scale versus the model scale, data scale is probability, model scale is logits. And here is the correspondence between the two. So a logit of 0 corresponds to a probability of 0.5. So that's the middle sort of agnostic point. If you have a probability of 0.9, so up here, that corresponds on the x-axis to a logit of 2, 0.2. If you have a probability of 0.1, so down here, that corresponds to a logit of minus 2.2. So it's symmetric about 0. Because if you start at 50-50 and you go up to 90% or you go down to 10%, that's the same change in logits, just opposite in sign. So if I have a probability of 0.99, that's a logit of 4.6. Can anybody guess what the corresponding logit would be for a probability of 0.01 down here?
Minus 4.6.
Minus 4.6, exactly. So if you know what a logit is for a probability of 1, you also know what the logit is for a probability of 0. You flip it, times minus 1. That is going to be really important to remember when it comes to interpreting what your software is doing. Because some software programs default to providing intercepts that predict the probability of a 1, and some software programs default to providing the opposite, which is known as a threshold. I've got that coming up here, which is the probability of a 0. So you will see things change sign based on what the reference is, whether you're predicting a 0 or a 1. And you can always get whichever one is missing by flipping the sign. So here's another picture. I stole this one from the Snyders and Bosker's multi-level book. This one shows the correspondence in terms of what a change in logits is for a change in probability. So the top measure here, this is the probability metric, which is bounded by 0 and 1. Technically it's proportion, but I keep saying probability because that's how people talk about it. The bottom here is the logit metric. So a probability of 0.5 corresponds to a logit of 0. In between these two is odds. So a probability of 0.5 corresponds to an odds of 1, which corresponds to a logit of 0. So here's why that is. Odds is probability of a 1 over probability of a 0. If they're equally probable, then odds are 1. If a 0 is more likely, odds are going to be between 0 and 1. And if a 1 is more likely, odds are going to be between 1 and infinity. So it's a weirdly asymmetric ratio. It is a ratio, it's not an odds ratio. I got to be careful with that. Erg. It's a weird thing. How's that? I'll just go with thing. So if I have a linear model that is predicting the change in y for a 1-unit change in x, the change in y in these models is in logits. So the logit can change in these increments, but they correspond to increasingly smaller corresponding changes in probability. So the linear slope, if I go back to this picture here, the same effect of x is not the same the closer you get to the ends. The effect of x has to shut off. So it's inherently a nonlinear effect of a predictor when it's predicting probability directly, even though it is still a linear effect when you're predicting logits. And actually, that's how I made this picture, is to predict the logit instead. So a linear slope on a linear model like we're used to thinking about is only linear in how it predicts the logit of the outcome. It is a nonlinear effect in terms of what it does to the probability. Okay. How are we doing so far? A few thumbs, a few stares, a few smiles. Okay to keep going, or any of that you want to hear again? Keep going? Good. All right, cool. All right. So this is one source of complexity when you're looking at your output. You got to ask yourself, am I in probabilities? Am I in odds? Or am I in logits? They all are related to each other, but they're not the same thing. So that's part of the problem. So if I use a standard general linear model to predict a dichotomous binary outcome, I can solve the line keeping going problem through a link function. The other problem that I'm going to run into, though, is what about the e's? So if I have a model that looks like this, and I were to compute what the e residual would be for any person, there's only 2 e's that are possible. Either you're off by 0, which is if you got a 0 by this much, or you're off from 1 by this much. So at any predicted probability, there's only 2 possible values for E. That cannot be a normal distribution if there's only 2 possible values. So the residuals cannot be normally distributed, which means that the standard errors from a standard regression model cannot be correct. They can't. The worst, like the best they can be is not that wrong, but there's no way they can be right. The other piece of it, though, is that a normal distribution has a mean that is separate from a variance. And I say a variance because I'm emphasizing the idea of singular. The residuals are supposed to be equally distributed at every point along the regression line. But that cannot happen in binary data. So if your model predicts that a given case has a prediction of 0.5, then the spread around that point in terms of the variance is 0.25, and that's the most it can be. The closer the predicted probability is to a 1, or predicted proportion, I guess. I need to start using the word better. The closer it gets to 1, the less variance you have to have around it. So in binary data, there is no separate variance. It's the proportion of people who got a 1 times the proportion of people who got a 0. So it changes along the predicted value. Fortunately, we don't have to work too hard to come up with something that's a better match than the normal distribution. It's our friend Bernoulli. So the likelihood function that is being maximized in binary data under a Bernoulli distribution is the probability of a 1 if that's what you got, or the probability of a 0 if that's what you got. That's it. It's the simplest one, especially relative to this thing, which has a kind of an ugly formula to it. So we swap out the conditional distribution of y to this one, and it has only one parameter, the mean to be predicted, and the variance is determined by the mean. So that means that residual variance is gone. We don't have it anymore. It's not a thing. That has a lot of consequences, though. So here are 3 different ways that you will see this model written. This is logistic regression that I am showing you. That is what it is called. Like, that's what the name would be on the menu for this meal. But then you go back to the kitchen and you look at the ingredients and you'd say, yeah, I need a logit link function and a Bernoulli conditional distribution with extra sauce. And they'd be like, one logistic regression coming right up. All of these things on this page are the same. I can't even tell you how frustrated I was when I finally figured this out. Because you see this and it's like, what? The difference is in what y is in each of these equations. So the top one, the reason that this looks like a standard linear model is because it's predicting logit y, the log of the odds of the probability of a 1. That's the link function, going from p to logit. Odds, if you take the log off of it, so exponentiate, unlog it, as I would tend to say, then you end up with a function that looks like this, where it's e to the linear model. And that gives you a predicted odds as an outcome. If you take that one step further and back translate into probability, that's the inverse link. So the probability of a 1, the model that you would predict it is e to whatever the logit's supposed to be over 1 plus whatever the logit is supposed to be. So this chunk right here is a predicted logit. E to the logit over 1 plus e the logit translates into probability. So this thing right here, where my mouse is, this is how IRT models are expressed. They all look like this. But secretly, they also look like this. Question?
So, like, if we're looking at like a characteristic curve, and we see like the S-shaped curve, if we took the log of that, it would be in terms of the first thing on this slide. It would be like the log of those values would result in a line if you were to re-visualize it.
Close.
Okay.
So the question was, if we took the curve that was on the page and we took the log of it, would we get to the line? It's that if the curve itself is predicting logits, it's a line.
Okay.
If x is predicting probability, it's that S-shaped curve.
Okay.
So these two then are actually equivalent mathematically. The -1 in the bottom makes these two the same. So if you will see Excel sheets where I have formulas written in here to like help you translate across these 3. I usually write it this way because it's less typing. But it's the same. So you can estimate this model in any software package, pretty much. I'm going to show you how to use Glimix, which is how you would do it in mixed effects models. Also proc Logistic, I think, not for this one, but for the categorical ones. In Stata, there's a package called Logit as well as GLM. And in R, we're using the GLM function where you can decide on family, and the family that goes with this one is binomial. Bernoulli is a special case of binomial when you only have one trial of 2 options, and link equals logit. So note what is missing from all of these equations that would normally be in with my linear model. What's not here? Error. Yeah, do you see any little E's or R's anywhere on the slide?
No.
Nope, it's gone. So it's not to say that the model is perfect. It's just that we don't put E at the end of these things because it doesn't have a separate variance. It's not a parameter. We know what E has to be. Yep, so there's no E's in here. All right. So in terms of going back and forth, the models that we will be estimating directly are going to give the predicted outcome in logits. So these are the parameters that are going to show up on your output. And in terms of how to interpret them, this is how I tend to talk about it. So beta 1 is the change in logit y for a 1-unit change in x1. Beta 2 is the change in logit y for a 1-unit change in x2. If you wanted to convert from logits into odds, you can do that. You can take your logit and unlogit it, basically down, exponentiate it, and then you're back to an odds as a predicted outcome. Likewise, these slopes, if you exponentiate them, e to the slope, those are known as odds ratios. So more definitions on those are coming just a moment. The point of this slide is to prevent you from doing these two squares right here. I see this a lot. And not just in students, by the way. I've seen someone who was presenting this in a workshop screw this up. Not throwing anyone under the bus. Just saying this is tricky. You cannot take a slope and convert it into a probability. You cannot do that. It doesn't work. Because a 1-unit change in logits, which is what a slope means, is not a 1-unit change in probability. It depends on where you are. A change from a logit of 0 to 1 corresponds to a change in predicted probability from like 0.5 up to like 0.73 or something. But if you keep following that out and you go from a logit of 1 to 2 and 2 to 3, those unit changes in logits correspond to increasingly smaller changes in probability. So you cannot take a slope and inverse link it back into probability. You cannot do that. It doesn't mean anything. The software will let you. It won't stop you from doing this. So I have an example of that as a cautionary tale. So predicted outcomes. You can take them from logits back into odds and back into probabilities, and that is what you would do to try and describe your model. So back to the idea of a predicted outcome. When I talk about what a model means, I talk about it in logits, because that's a formal, like, this is a slope, this is an intercept. But then you get to y, and people are like, what the hell is a logit? And you could say, well, I know that if a logit is positive, that corresponds to a proportion between 0.5 and 1. And a logit that's negative corresponds to between 0 and 0.5. I know that. But otherwise, I don't have a sense of that. Nobody knows what odds really is either. But people know what probability is. That one people can handle. So what ends up happening as a strategy is you can talk about your model results in terms of what they do to the logit. But when you make your picture to describe what your model predicts, that y-axis should probably be in probability. But it does change what the picture looks like from a linear slope to a curvilinear slope, which can be confusing. All right, speaking of can be confusing. Okay, how are we doing? Any that you want to hear again or differently? Rumors? Zoomers? We decided that the name for in-person people is going to be roomers, like R-O-O-M-E-R-S. As it, not like rumors, like I'm spreading rumors, but, you know, being in the room-ers. Okay, couple thumbs. All right. So here is yet another way that you will come across people talking about these models. So we're up to like 4 now. And one is this idea of Y star. Well, you see, what if we didn't really have a binary outcome? What if we, like, underneath it, like secretly, like latently, it was a continuous variable and we just measured it dichotomously? What if? And you're like, yeah, you're just making shit up. I know, but that's what Y star is. So people will refer to the idea of a latent response, where latent does mean imaginary in this case because you do not have that information. And they'll talk about Y star as the model outcome, and that translates into the linked metric. So Y star is in logits. And in this description of it, you will almost always see, rather than an intercept, something called a threshold right here. The threshold is an opposite of the intercept. So whereas the intercept would give you the predicted outcome of a probability of 1, the threshold gives you the predicted probability of a 0. So they're opposite in sign. A threshold times -1 is an intercept. So if you estimate these models in M+ software, for instance, and if you're doing an IRT model, you get a threshold. If you estimate these models in O-Logit and Stata, you get a threshold. If you estimate these models in Proc Glimix, you get a threshold. You can override it to get an intercept. So that's one of the complications, is trying to figure out which way this goes. And that is why in every example that I'm going to show you in this class, the first thing we're going to fit is an empty model. A model with no predictors, because I know what the answer is going to be then. If the answer back translates into the proportion of cases that have a 0, then I'm getting thresholds. If the answer back translates into the proportion of cases that have a 1, I'm getting intercepts. So you always got to figure out which way is up to start with these things. So in this description of Y star, people will have an E on the end of it. Because then we're saying, well, Y star follows a logistic distribution. And here's some logistic distributions I stole from Wikipedia, where the mean of a logistic distribution is 1 parameter, and the variance is pi squared over 3. It's a constant. It works out to be 3.29, give or take. And then in the logistic distribution, you also have another parameter that's for over-dispersion, but in binary data, that's fixed to 1. So in this representation of it, you will see residual variance of Y star being fixed at 3.29. We do not have the underlying variable. We only have the binary version of it. So this doesn't make a lot of sense practically speaking, because you can never know if the underlying variable follows a logistic distribution because you don't have it. But this is where this number comes from. You will see this number periodically because people use it to try and hack their way into some kind of R square. Because now I've got a variance and I can work with that number to try and talk about variance explained. Question?
So if we're using this test to meet ability with IRT, then that's assuming that ability follows a logistic. No. Okay.
No. In IRT models, ability is X, not Y.
Oh, okay. Yeah.
And X in IRT models is also a latent variable. It's supposed to be normally distributed, multivariate normal in models with more than one latent variable. But we're talking about Y.
Okay.
Yep. So you will see this 3.929 creep in here, and this is where it comes from, is this idea of this continuous underlying distribution that Y star characterizes, that has an E to it. Here's another one with respect to the scale of the underlying distribution. There is a cousin to logistic regression called probit regression. Probit is another link function. The goal of probit, just like the goal of logit, is to create an unbounded outcome that can be predicted by a line that goes on forever and ever. Probit looks like this. In English, a probit is a z-score. Do you remember back in like intro stat textbooks where like in the back of the book they'd have like a z table and you look up your z and then there's like the probabilities in the table and then you'd have to answer homework. So it'd be like, well, for a z of this number, what's the probability that goes with it? And then if you have a probability of this, what's the z-score? A probit is the z-score that goes with the area to the left of the curve. That's what it is. So it's in a different scale because this is based on a standard normal distribution where the variance is 1, not 3.29. So probit regression does the exact same thing as logistic regression using a different scale for the underlying pretend y star variable that you don't have. For those of you in IRT class, probit is ogive. Same thing. Now you might be thinking to yourself, Lisa, if this underlying variable is latent and we don't have it, then how can you tell me it has a variance of 1 or a variance of 3.29? We don't have it. And I'd say, yes, that is correct. So should you care about this? Probably not. For those of you who are new to my vernacular, pry is an expression that means probably. It's a shorter. Like, I'll probably go to Hy-Vee later to get more Diet Mountain Dew. It's a shorter way of saying probably. Probably is also acceptable as a substitute, but it has more letters. So should you care about this? Probably not. So here's the difference in what y star is thought to look like according to each of these models, where a probit model says y star follows a normal distribution with a mean of 0 and a variance of 1, and a logistic underlying y star says, no, it has a variance of 3.29. But if you convert these two by a factor of 1.7, can you see the difference between the black line and the red line? Nope. They make the same predictions. It don't matter. And like it might matter just an eensy tiny bit for a little bit of this, and I don't have room in my head to care about that. I just don't. I'm sorry. I got too much up there already. I can't store this. So in practice, which link function you pick does not really matter. But if you're working with results from a probit regression versus a logit regression, they're going to be off from each other by a scaling factor of 1.7. The 1.7 also shows up in IRT formulas, by the way, to go between a logit version of the model and the ogive version of the model. Fun facts about probit. Also, there's no such thing as an odds ratio in probits because it's not based on odds. To go from a probit to a probability, you have to integrate the area under the curve. So it's not as easy to go back and forth between the predicted outcome by the model in a link and to unlink it to go back to probability. So my understanding of this is that probit actually came first, but somebody figured out that logits were mathematically way easier to work with and that you could rescale them to get the same thing. And so logit is like the way of the world now. So you will occasionally see probits in structural equation models and IRT models for categorical outcomes if you use what is known as a limited information estimator. So where it's based on a summary of the responses instead of the original responses. Those models are only available in probit flavor. They don't have logit flavor. So sometimes you may get stuck in probits rather than logits because that's the only choice your software gives you. But otherwise, 1.7 to get back and forth. It doesn't matter. So did I not warn everybody here that what the hell y is why these models are hard? Because you got logits, you got probits. If you got logits, you got odds. Either way, you got probabilities. But then you got to figure out if your model's giving you the probability of a 0 or a 1, or some mishmash of both, which also happens. So figuring out what y is the hard part of these models. If you get that done, you're home free. And then there's two more that I want you to have heard of, but that we're not going to get a chance to play with in class. So both of these functions, logit and probit, are symmetric. They predict that the curve as a function of some x predictor goes away from 0 at the same rate on either side. So now I have to do like my walk like an Egyptian pose to do the S-shaped curve. For those of you who were not born in the 80s, you need to ask the Google about the song Walk Like an Egyptian by the Bangles. Everyone walks through the video doing this, and that's what I'm doing. So this is my logistic walk like the Egyptian thing here I'm going here. But this is symmetric in logits and probits. In other types of models, you may find data in which ones are a lot more common than zeros, or vice versa. And so there are other link functions that are thought to work better for those cases. So logit and probit are shown by the blue-purple line here that's right on top of each other, because once you multiply by the 1.7, they're on the same scale. Log is the name of the link function that you might prefer if you are predicting a binary variable that has a lot more ones than zeros. So if we follow the red line here, the red line looks almost exactly like logit and probit until you get down to 50-50 or so, and then it just kind of dies off. It stops shutting off. So this is kind of like an acknowledgement that if you don't have very many zeros in your data, the prediction in that range is probably not going to be as good. So the curve really focuses on the front half as what the predictor's effect would be indexed by, and the back half is kind of just like left alone. The other one is the green one, which does the opposite. The complementary log, which looks like logit and probit on the low end, but then it kind of shuts off like the red line on the high end. So complementary log is for outcomes in which 0 is more common. Yes, sir?
Will logit work regardless, though?
It'll work. Logit will work regardless in the sense that you will get numbers. Whether or not those numbers do as good a job of predicting the zeros and the ones is sort of an open question. You can compare across logit, log, and complementary log models using AIC and BIC, information criteria. Smaller wins. And honestly, I can never, ever remember which is which. And every time someone asks me about this, I have to get this slide out and look myself. So don't ask me to remember this off the top of my head, because I won't. So log, outcomes that 1 is more frequent. Complementary log is when 0 is more frequent. And in practice, when I've looked for these things in software, what I often see is that a software package will only have one and not the other. And if you go into its documentation, it'll be like, well, we have log, so if you need the other one, just flip your data. Like, I'm not going to program both of them for you. Further adding to the complexity of what y is. And in these distributions, the pretend underlying continuous variable that you don't actually have, but we're going to pretend like you have it, has a variance of pi squared over 6. It's characterized by a Weibull extreme values distribution instead. So, same idea. Yeah. All right. Farhan, I see the scary smiley face you put in the chat window. I'm not sure at what point that went in there, but is there a question behind the scary chat window face?
No, not right now. It's just a lot to digest.
Hard to digest. Yeah, it is. But this is why we make the big bucks, right, folks? You learn this stuff, someone will pay you so that they don't have to. Question?
So is phi or phi, however you pronounce it, is that the same one that IRT defines with in respect to, there's a lot of like new terms that are floating in my head.
There's a lot of words, yeah.
I guess the general question is, can you assign different meanings to different Greek letters? Or is phi something specific?
Oh, so the question was, what is phi in this slide? And is it the same thing that it might be in someone else's notational system? It's always something new. All
I wish-
notation is author and context specific.
I wish there was a standard for it, because
I know.
that's...
This thing, though, I think this stands for like the cumulative normal, standard normal distribution function.
Okay.
Like, I think it has that meaning, as opposed to like, you know, the Greek letter that I look at, I picture like on the size of a frat house or something. That's where I picture this in my head when I see it. But yeah, unfortunately, no. Letters get reused. Greek letters, regular letters, Roman letters. Yep. Okay. So I know there's a lot of new vocabulary and a lot of new words here, but let's focus on the big picture before we eject for the week. What are we doing? Let's back up. I'm going to stop the screen share so you can all see each other here as I ask this question. No, hang on. No, stopping. There we go. What are we doing? There we go. Now none of you can see any of the slides. What are we doing? Yeah.
I would say that we're trying to predict possible values when we cannot assume normal distribution of the possible values using a linear predictor.
Yeah, that's a good answer. We are trying to say it again. I just lost it.
Predict or estimate
Predict or estimates.
values or outcomes when we cannot assume a normal distribution of those
Yep.
of the residual variance of those possible outcomes.
Yeah, we're trying to predict possible outcomes when what is possible doesn't follow a normal distribution. I'll say that. Yeah, we're trying to predict binary outcomes today, but eventually other kinds, right? And there's two things that we got to fix to do that. So we had, Cassandra, you said model transformation. Do you want to elaborate on that? What's being transformed?
Specific to the link functions, so going from logit to, sorry, scrolling through notes, logit to probability, and then taking inverse. If you want to go back to logit and try the ops.
Yeah, link functions, they are transforming not the data, they're transforming the model predicted outcome to be more continuous. So logit is one kind, probit is another, complementary log-log and log-log are yet others, but all of them do the same thing. They create an outcome that ranges from negative to positive infinity that can be predicted with a linear model. And all of them, when you back translate to probability, keep the probabilities predicted between 0 and 1 like they're supposed to.
So essentially, like if we have an introductory stats student say, oh, I have this binomial outcomes, or sample with binomial values. I'm trying to fit a linear model to this, and you say no, that's not a nice way of doing it. There's a better way.
Yeah.
That's
Yeah,
the
so
simple way of saying it.
if you have a binomial outcome, like number correct on an exam, what's the best you can do? All of them correct, right? 100%? What's the worst you can do? None of them? That sounds like boundaries to me. Same problem. And actually, logits are used for binomial outcomes too, but just with a different error distribution. So that's the other part of it, besides the link function, is we're not going to say that errors are normal. We're going to say the errors are Bernoulli. And that means that there is no separate error variance, and that is dependent on the predicted probability, the conditional mean. That's the big picture, but the devil is in the details. Okay, any other questions before we wrap up?
Would you say that link functions is a way of transforming categorical data into continuous data? Is that accurate?
I would say link functions are a way of transforming the model predicted mean of categorical data into a continuous. Like you can't say the data.
Yeah.
Because actually if you try to do a logit transform on binary data, it's undefined.
Okay.
because it asymptotes at 0 and 1. It doesn't have a corresponding logit. So you're transforming the probability, like the conditional mean. You got to keep that middle step in there, even though it's like conceptually, it's not a thing you're used to thinking about. Okay. Then it was not garbage day. That means it's Thursday. That means I say, have a good weekend, everybody. Thanks for being here. Let me know if you need anything. Homework's due Monday. Good luck with that. Bye, folks. See you next week.